Hi everyone, this is going to be our last lesson on calculus with the Maclaurin series. So when we're working with the Maclaurin series, we can integrate and differentiate just like we do with any regular polynomial. If you remember polynomials, when we go to integrate and differentiate with them, we're just using our power rule, which is great. So that makes our Maclaurin series approximation very simple to integrate. But this is, again, helpful for us if we're working with a very complicated integral, very complicated function, where we can't write it in just generic indefinite integral form. So in this lesson, I have 3 examples for you, so stay tuned. It's going to be quite a lengthy video for us today. There are more examples in your textbook, so feel free to take a peek at those. But for now, we have the Maclaurin series for cosine x is given to us, and we want to find the Maclaurin series for sine x using differentiation and integration. So I'm going to start off with the differentiation component. So the first thing is I know that the derivative of cosine x is equal to negative sine x. So if my goal is to solve for sine x, I can say that sine x is equal to the opposite sign of my derivative of cosine. And I can follow this Maclaurin series expansion and substitute that in for where I see cosine. And then I'm differentiating, or I'll get there in a minute. All right, so when we're working on differentiating using the Maclaurin series, notice how our summation starts at 0. When we're differentiating, we actually want to start at k equals 1. So we're going to separate the first term from the rest of the summation. You'll see why we do this in a little bit, but every single step, every time you're differentiating, we want to separate out that first term. So if I plug in 0 in for this, I have negative 1 to the 0 power, and then I have x to the 0 power over 2, 0 factorial. So this is just going to simplify down to 1, and then my summation is going to start at 1 now because I'm pulling that first term out. Again, you'll see why we do this later, but for now, we'll get in the habit of just separating out that first term. All right, now if we think about our summation, these 2 parts right here represent constants. So when we go to find the derivative, the only part that we're going to pay attention to is this right here. And my example is if we think about, if we wanted to find the derivative of 3x to the 4th, we want to find the derivative of 3x to the 4th. Technically, the 3 is just hanging around. So really what we're doing is 3 times the derivative of x to the 4th. So I would have 3 times 4x cubed. So just keep in mind that that's what we're doing here. So when we're working with this summation, we're only going to be finding the derivative of that x component. So I'm going to separate this a little bit. I'm going to distribute my derivative component. So I'm going to find the derivative of 1, and then I'm going to add this on. I'm going to find the derivative of just that x component. So my negative 1 to the k, 2k factorial, that's just hanging out. Really what I'm only doing is finding the derivative of x to the 2k power. So I know that my derivative of 1 is just 0, and the negative of 0 is still 0. So now what I'm going to do is I'm going to change this sign right here to be, actually, I forgot to distribute in. When I distribute, this negative sign goes to the positive, makes this sign negative. Now I don't want to deal with the negative summation. I want to end up dealing with a positive summation. So what I'm going to do right now is I'm going to say that this is equal to k equals 1. I have negative 1 times negative 1k, 2k factorial, and then I'm going to leave my derivative alone for now, x to the 2k. So again, all I did at this step was I said, okay, this negative is actually just negative 1. I'm moving it there so I can change this to be a plus sign. Now I notice that this is an exponent of 1, so what I can do, I'm going to use some Hermitian privilege right now. I'm going to change this term, and I'm just going to say that this is negative 1k plus 1. So that way I can get that positive sign and also combine my two negatives. Now I still have to differentiate, so let's make sure we're doing that. I'm going to duplicate this down. I don't need this negative, I don't need this 0 anymore, so I'm just going to take that off. Now when I go to actually find the derivative of x squared to the k power, I know that I'm going to bring my 2k down, multiply by x, and then my new exponent is going to be 2 times k minus 1. So I have my 2k and then x to the 2k minus 1. Now I want to simplify this as much as I possibly can. So I'm noticing right here that I've got 2k factorial in my denominator, and then I have 2k up in my numerator. So we've talked about this when it comes to factorials. So let's say, just for example, I have 8 over 8 factorial. 8 factorial is equal to 8 times 7 times 6 times 4 times 3 times 2 times 1. So I have 8 over 8 times 7 times 6, and this is going to continue. If I cross my 8s out, I'm left with 1 over 7 factorial. We've talked about that before. So to simplify this just a little bit more, k equals 1. I have negative 1 to the k plus 1 power. I still have my x to the 2k minus 1. And now my two pink components, I'm going to change this to say 2k minus 1 factorial. So those two pink parts become this pink part right here. Now I want to go back to where I said we can't start this summation at 0 quite yet. And I want to show you why. This is why we took out our first term. If I say, let's just say, if k equals 0, in this current summation, I'm going to have negative 1 to the 0 plus 1 power, and then I'm going to have x to the negative 1 power all over 2 times 1 minus 1 factorial. So this is going to simplify down to negative x to the negative 1 power over, this is minus 1, over 1 factorial. And I can't have x to the negative 1 power. Our summations don't work that way. We only have our integer, our positive integer exponent. So this is why we had to take out that first term. So since we're not able to start at 0, at k equals 0, we're going to get a little bit crafty, and instead we are going to let n equals k minus 1. So what that tells us is that n plus 1 is equal to k. So I'm going to say that my summation, now I can start it at 0, because I do want my summation to start at 0. I just can't let k equal 0, but I can let something else equal 0. So now I'm just going to take all of my k's and I'm going to change it and convert it to an n plus 1. So I have negative 1 to the n plus 1 power, and then I'm going to have x to n plus 1 minus 1 all over 2 n plus 1 minus 1 factorial. Just to make this a little bit cleaner for us, n equals 0 to infinity. I'm going to have negative 1 to the n plus 2 power, x to the 2n plus 1 power, and then 2n plus 1 factorial. Just to focus in on this part a little bit right here, just a reminder that if I have negative 1 to the n plus 2 power, what this is actually saying is I have negative 1 to the n power times negative 1 squared. Now, I know negative 1 squared is always going to be positive, so I don't need this plus 2. I can just take this out and leave it to be plus n, because this is always just going to be 1. All right, so again, our goal was to find sine of x as a Maclaurin series expansion, and that is what we just did. We used differentiation to get sine x as the Maclaurin series expansion. So we're going to do the same process again, but with integration. So for part B, I know that when I go to integrate cosine x dx, I get sine x plus c. Now, when we're working with integration, we always want to be working with a definite integral. We don't have indefinite integrals when we're working with Maclaurin series expansion. So if my goal is to get sine x, what I'm going to do is I'm going to create an integral where my bound includes an x. So I'm going to say cosine t dt, and then I can say that this is equal to sine x minus sine 0, which is equal to sine x. So I'm going to use a little bit of a workaround here. So, and maybe you're noticing, I know what my integral of cosine is. That is given to me in my IB formula booklet. So I can say that sine x is equal 0 to x. Instead of cosine, I'm going to replace this with negative 1 to the k power, t to the 2k power, and then 2k factorial, and then I'm differentiating with respect to t. Again, this is from your IB formula booklet, so check for that to see where your Maclaurin series expansion for cosine comes from. I actually forgot the summation part, so I'll have to add that in there. K equals 0 to infinity. Now, if we remember from the last example, we're really only taking care of the t part. We don't really care about anything else. So I'm just going to reverse the order of this. I'm going to put my summation on the outside. So I'm starting at 0 this time, and then I have my integral from 0 to x, negative 1 to the k power, t to the 2k power, 2k factorial, and then dt. If you want to separate it into the two components like we did last time, you can definitely do that. I'm just going to leave it as 1 for the sake of ease, I guess. So I have infinity, k equals 0. So now I'm ready to integrate. So again, my constants are going to stay the same, my coefficients stay the same. The only thing I'm integrating is this component right here. I know when I integrate, I add 1 to my exponent, and then I divide by the new exponent. And this is a definite integral, so I'm evaluating between x and 0. So I'm going to put my brackets in here. So now I can go ahead and substitute in my x and my 0. I know if I substitute in the 0 for t, I'm going to get just 0, so I only need to substitute in the x part. Now just a reminder, we integrated with respect to t, so this x and 0 are only going to go in this spot. We don't substitute where the k's are. So everything else stays exactly the same. I'm just replacing my t with an x. So I have negative 1 to the k power, x to the 2k plus 1 power, and then I can change this to say 2k plus 1 factorial. And if you notice, this answer does match what we found for our previous problem. This time we used n instead of k for sine x, but in both situations we do get the same answer. We can say that x belongs to the set of all real numbers. So that's our first example. Moving on to our second example. I'm going to move these over just a hair so I can give myself some more room. All right, so the next example, we're going to look at the Maclaurin series expansion for cosine, and we're going to use this to find cosine of x squared. Now, we talked about composition of functions in our previous lesson, so if you're not quite sure how compositions work, you can go back and rewatch that video. But we know for part A that cosine of x squared, it's going to be the exact same thing for cosine, but we're just replacing all of my x's with x squareds. So looking at the same expansion that we used in part A, I have -1 to the k power x squared to the 2k power over 2k factorial. Now I can simplify my numerator just a hair. I can say that this is equal to x to the 4k power. All right, so this is my full and complete answer for part A, so I'm ready to move on to part B. So remember, I have to use a definite integral when I'm working with a Maclaurin series expansion. So I'm going to estimate the area under the curve of cosine x squared from 0 to 1. So I'm going to set up my integral from 0 to 1. I'm going to use my Maclaurin series expansion for this. I'm using my answer from part A. Remember, whenever you see that word hence, you're using your answer from the previous problem to help you out. So -1 to the k power, x to the 4k power, over 2k factorial, and then I'm throwing my dx on there. For this one, I am going to separate my integral, so I'm just going to focus on this second part. So my summation, k equals 0. My constants, I'm just going to bring out front, 2k factorial, and then I'm really only focusing on this part right here. Now when I go to integrate this, remember I'm adding 1 to my exponent and dividing by the new exponent. So again, I'm just going to copy this down. So when I go to integrate, this is going to turn into x to the 4k plus 1 divided by 4k plus 1, and then I'm evaluating between 1 and 0. So when I go to substitute this in, k equals 0, -1k, 2k factorial. When I go to substitute this in, again, I'm only substituting in for x. So I have 1 to the 4k plus 1 power all over 4k plus 1, and then I'm subtracting 0 to the 4k plus 1 power all over 4k plus 1. Just to copy this again, 1 to anything is just 1, so my numerator becomes 1, and this term ends up becoming 0. 0 divided by anything is just going to be 0. Now I can combine this into one summation. So again, starting at 0, -1 to the k power, 2k factorial, and then I can extend this to say 4k plus 1 is going in my denominator. Now you might be wondering why we're able to do k equals 0 this whole time. Remember, just when it comes to differentiation, that's when we need to take out that first term and start our summation at 1. When we're integrating, we can go ahead and start at 0. So this is my Maclaurin series approximation. Now I'm going to use that to estimate to 4 decimal places. So I actually want to figure out what that area under the curve is going to be. So what I'm going to do is I'm just going to start making my terms. So if I plug in 0 in for k, I get -1 to the 0 power over 0 factorial, 0 plus 1, and I can repeat this process all the way down. So -1 to the first power, 2 factorial, then 4 plus 1. I'm going to continue this process until I reach enough terms. So 2 times 2 is going to give me 4 factorial, and then I have 8 plus 1. So this is going to continue down and down the line. Now just to summarize or simplify this a little bit more, I'm going to have 1 minus 1/10 plus 1 over 2/16 minus 1 over 9,360. There we go. I'm adding my terms as I go. So you're maybe wondering, well, how do I know when to stop? You stop when you add another term and your answer is the same, rounding to 3 significant figures. So obviously I'm just adding these two together. I'm going to get 9 over 10. If I add this, my answer is not 9 over 10. It's something completely different. So if your answer for this and this is the same to 3 significant figures, then you can stop. So my answer, my approximation is 0.905. So that is how you know that you are ready to stop. So that is our second example. We're going to move on to our very last one. All right, our last example, we're going to use the Maclaurin series for 1 plus x to the p power to find the Maclaurin series for 1 minus x squared to the negative 1/2 power. So in your formula booklet, actually I don't think this is in your formula booklet, but it's in your notes. It's just your binomial expansion. So from your notes, we have 1 plus x to the p power equals 1 plus k equals 1 to infinity for p minus 1, all the way up until we get p minus k plus 1. We divide by k factorial and then times x to the k. So this is a set formula. You won't need to come up with this on your own. Now we have a composition here, so I don't want 1 plus x to the p, I want 1 minus x squared to the negative 1/2 power. So everywhere I see an x in this equation, I'm going to substitute it with a negative x squared. And also everywhere I see a p, I'm going to replace it with a negative 1/2. So my Maclaurin series expansion for this is going to be 1 plus my summation k equals 1, so I have negative 1/2, negative 1/2 minus 1. These terms are continuing until I get negative 1/2 minus k plus 1 k factorial, and this term changes to negative x squared k. So just to show you again, my negative 1/2 is just replacing all of my p's, and my negative x squared is replacing all of my x's. Now, of course, we can't leave our Maclaurin series expansion like this. We need to simplify this down as much as we possibly can. So the first thing I'm going to do is I'm going to focus on, let's see, on my x squared to the k power. I'm going to focus on that real quick. So I'm going to copy everything down. Everything's going to be exactly the same for this problem. The only thing is I'm going to change this to say negative 1 to the k power and then x squared to the k power. The next thing that I'm going to do is I notice for this expansion that there's a couple different patterns happening. First off, I have a negative in every single term that involves my p. So I can factor out a negative 1 for all of those terms. I also notice that I have a 2 in the denominator of every single one of those fractions. So I can go ahead and factor out a 2 from my denominator. I am going to simplify this term while I'm here. This term is going to turn into 1/2 minus k. So to take care of that oscillating sign, I do see that I have negative 1 to the k power for all of these terms. And then I also have this negative 1 to the k right here. So both of those I can write as negative 1 to the 2k power. So again, that's taking care of all of my negatives. This should be k factorial in my denominator. So k factorial. Now if you mention, every single term is divided by 2. So every time I'm dividing by 2, and there's k of those terms. So 2 to the k power is going to take care of the bottom part of that fraction, that denominator. Now in my numerator of these fractions, what I'm left with, this is negative 3 over 2. We'll see this pattern. All I'm left with is 1 times 3 times 5, and that continues until I get to 2k minus 1. And then don't forget, I still have this x to the 2k off on the end. So I did a lot in this step. So just as a reminder, I took care of my negatives. My division of 2 in my numerator was taken care of in this step right here, and then I'm left with 1 times 3 times 5. Now, we have factorial. Factorial is helpful for 1 times 2 times 3 times 4 times 5, but we don't have a way of representing 1 times 3 times 5. So we're going to get a little crafty here, and we're going to say that actually, the first thing I'm going to do before I do that, I'm going to copy this all down, repeat this same step. You may notice here that I have negative 1 to the 2k power. So this is always going to be even, no matter what. This term is always going to be even because I've raised to an even power, which means I can just get rid of that whole thing, which is great. All right, now focusing what's left of my numerator. Again, I don't have a factorial for just odd numbers. I only have factorial for my full set of numbers. So what I'm going to do is I'm going to multiply this whole thing by 1. However, my 1 is going to look a little bit different. I'm going to multiply by 2 times 4 times 6 times 8 all the way up until 2k. Now the reason I'm able to do this is because I'm going to do the exact same thing in the denominator. This is equal to 1, so that's why I am allowed to do this. I can multiply by 1 and I still say exactly the same. Now my reason for this, now in my numerator of the summation, now I have 1 times 2 times 3 times 4 times 5 all the way up. So I have 1 plus my summation, k equals 1. Now I can write this as 2k factorial. And then I'm left with still my x to the 2k power, and then I have 2 to the k power, k factorial. And my denominator, I'm left with 2 times 4 times 6 all the way up to 2k. So my denominator is still here, but I've taken care of everything else. Now what I'm going to do in my denominator is in those parts, I'm going to factor out a 2. So I can say that 2 times 4 times 6 all the way up to 2k, I can rewrite that as 2 times 1 times 2 times 3 all the way up to k. Now maybe you're seeing where this is going to go, because this now I can represent as k factorial. I'm going to simplify my summation a little bit more, so I have 1 plus, going to infinity, starting at 1. I have 2k factorial, x to the 2k power, 2 to the k power in my denominator. This is actually 2 to the k power because I don't just have 1, 2, 2. I took 2 out from every single term. There are k number of 2's. So I have 2k, my 2k from before, and I actually have 2k factorial. So I can write this as k factorial squared. All right, and then lastly, I can merge these two terms together to say 4 to the k power. Now this is my fully simplified version for part A. Now, of course, there's a part B and a part C for this equation, so that was just, or this problem, so that was just part A. Going back to part B, I want to use the fact that arc cosine x minus arc cosine 0 equals the integral from 0 to x of -1 over 1 minus t squared dt to find the Maclaurin series for arc cosine. So I'm going to use that information to help me figure out what my Maclaurin series is for arc cosine. So for part B again, just to write out my given, arc cosine x minus arc cosine 0 is given to us as this. Now, you may be thinking, wow, this looks literally like nothing like we just did. Where did this come from? Now, if we think about the previous problem, previously we were working with 1 minus x squared to the -1/2 power. This is pretty darn close to that. I just threw a negative out front, and now all of a sudden this is the same thing. But I don't have x, I have t. So I can rewrite this. Arc cosine x, we know that arc cosine of 0 is pi over 2, so I can write this as pi over 2. And then next I can bring this over to the other side, so I can say equals pi over 2 plus my integral. All right, and now I'm ready to integrate. So I have pi over 2 plus my integral from 0 to x. But I'm going to replace this with my Maclaurin series expansion. So I can say infinity k equals 1. I'm starting this time with k equals 1. We got that answer, or actually just kidding. We have to start with 1 plus k equals 1. This is our solution from part A. So 2k factorial, and then t to the 2k, actually there's no factorial there, t to the 2k over 4k, and then k factorial squared. Again, this is our answer from part A. So now we can go ahead and integrate. So I have pi over 2, and then I can say pi over 2, and then plus, I'm going to do from 0 to x of 1 dt. Actually, we can't forget about this negative out front from up here, so don't forget our negative. So I'm going to actually change this to a minus. So minus 1 dt, and then plus my summation from k equals 1. I have my 2k, 4k, and then k factorial squared, and then I'm actually integrating from 0 to x of t to the 2k dt. When I go to integrate, I left with pi over 2, and then minus t, I'm evaluating between x and 0, and then I have plus my summation starting k equals 1 to infinity. Again, this part stays exactly the same. Cancel. Duplicate. There we go. And then I'm just integrating with respect to t. So I'm going to have t to the 2k plus 1 all over 2k plus 1, and then I'm evaluating between x and 0. I'm going to go ahead and substitute in my values for x and 0. When I substitute in 0 to both of these, I just end up getting 0. So I'm going to replace all of them with just x. So I have x to the 2k plus 1. And now I'm going to simplify as much as I possibly can. I'm looking at this, and actually I don't really see anything else that I can do right here. So this is going to be my Maclaurin series approximation for arc cosine. So I have pi over 2 minus x plus my summation that I am given. Now the last part of this problem is I need to use this to approximate the first 3 terms. So for part C, I know that arc cosine of x is equal to pi over 2 minus x plus my summation of k equals 1 to infinity 2k all over 4 to the k power k factorial squared, and then times x to the 2k plus 1 over 2k plus 1. Alright, so I need to find my first 3 terms. Lucky for me, my first 2 terms are already given to me. So pi over 2 and x are my first 2 terms. Now I just need my third term. To get my third term, I'm just going to substitute in 1 for k. So I have 2 times 1, 4 to the 1 power, 1 factorial squared, x to the 2 plus 1 power, and then I also have 2 plus 1. So this is going to simplify down, x over 2 minus x plus 2x cubed over 12, which then will simplify down to pi over 2 minus x plus 1/6 x cubed. So the first 3 terms of this polynomial expansion are given. If I wanted more terms, I would continue to use the rest of that summation. So again, the notes have plenty more examples for you to practice with integrating and differentiating the Maclaurin series, and come see me if you have any questions.